All right, back to software engineering, already in progress. Yes.
Can we switch some of the lights off so that?
Yes, we can. I have a power switch over here. Let's see. Ooh, nice. Ooh, nicer.
Yeah.
Nicer. Nice. Wow, now we're in style here. Okay, so let's go. I'm going to go through a lot of lectures here. I'm going to talk about software reliability, software dependability, how to estimate, how to cost software, testing, and I have I think I'm missing another subject, but we'll see. Quality assurance, testing qualities of software. Oh yes, that's what I was missing. Architecture, software architecture will be the last subject. So right now I'm going to go through reliability, dependability, and maybe we'll see how far it's still early. Security as well as part of the other topics, and we'll break in. It's about 10:35, 11:30, about noonish. If you have to go to the restroom, please just get up and go to the bathroom. With all of these distractions and the interruptions that are going on, it's just kind of like a free-for-all today anyway. So it's not going to bother me. We don't have to wait for a break. You can go ahead. If the bathrooms are actually located on the second floor of this building, it took me a while to find them. So you go up the stairs, hang a left. I believe there's a men's and a women's room up there. The one down here, I think they're doing something with the floor. They're cleaning it or something, so. Anyway, we'll see what happens. Or I might actually break before noon. Depends, I guess, on how long I last as well. So, any questions before we get started? If you came in a little bit late, if you're brand new to the class, come see me at lunch hour, and I can fill you in on everything you missed. If you are not brand new, but you came in late and didn't hear any of my announcements, nothing is due until the very last day of the term, which is May 9th. So, you haven't missed anything yet, so you can still turn your stuff in. All right, software reliability. What does it mean to make reliable software? Dependability and reliability systems. This is an example of you can read through the slide on your own. It's slide set number 6A if you download it, which is available from bhacker.com. So this is an example of what could happen when you try to make something dependable. And I'm going to talk about dependability in the next lecture, but it's hard to talk about what the differences are without mentioning it, at least by definition. If it's dependable, it usually means it's reliable. But those are actually two separate qualities. If it's reliable, it's up 24 hours a day, 7 days a week, always accessible. So when I think about reliability, I often and this will help you with the midterm actually if you're taking notes, I always think about accessibility. I also think about accuracy when I talk about reliability. If something is reliable, I can trust it. And I have this perception of it being accurate, available, accessible. I can get to it, I can reach it. Because it might be available and I might not necessarily be able to reach it. I might not be able to have accessibility to it. It has correct information. I can bet my life on it. If I'm driving in a car, I want my brakes to be reliable. Because I want to know that I can avoid a problem if one exists. So what's dependable? If it's dependable...
The GPS system?
I'm sorry?
The GPS system of the car, it should be dependable. Is it correct?
Yeah, I would say reliable and dependable. Can I rely upon something to... Can I rely upon it to give me the correct directions? When I depend on it, it means it has to be available. It has to be reliable. It has to have all of those other... So dependability I put kind of as a category of reliability, yet it does mean something extremely different. Meaning, if I were to jump out of my airplane with a parachute, I need that parachute to be dependable. If the parachute doesn't open up, I'm hosed. If I'm wearing a heart monitor that's electrically doing something to make sure my heart's running or something, I need to depend on that. So when I think about dependable qualities in software, what makes it dependable? Well, if we have multiple ways of doing something, so if we can't rely on step A, algorithm number 1, and we can't rely on algorithm number 2, we have algorithm number 3. By having 3 algorithms, that software is dependable. We have an ATM. If this ATM is broken, we can go 2 blocks and get another ATM. So it's dependent. I want coffee in the morning. If I drive up to Starbucks and they don't have any more coffee, I can go to another Starbucks. I can go to another. So having multiple locations makes Starbucks dependable because we know that it's going to, hopefully, there'll be a Starbucks around. We can't necessarily rely on the first one being available or the second one being available. So we build dependability in to make it so that we can use that system. Like we have the ability, like for example, we have cars, we have trains, buses. It's dependable transportation because we have different options. If our car breaks down, we can call a cell phone and get a taxi or something. Or actually, hopefully we won't have to call, we just wave one down maybe, especially if we're in San Jose. Which means it's dependable. So they think, is your car dependable? It's usually can you depend on it? Do you have a dependable mode of transportation? Yeah, it breaks down occasionally. Can't always rely upon it being 100% correct, but if it doesn't work, I have to take my bicycle. So I have reliable / dependability. So as we go through the lecture, I'll talk about both of them. And this particular lecture is on reliability. The next one is on dependability. So if you can kind of just formulate your own, and this is one of those interesting characteristics about software engineering is that you can't, it's not like cut and dry. It's left to interpretation. And what we're going to find out is left to user interpretation. It doesn't really matter what the development team thinks. It's the user's perception that's the most important. So in this particular example, if you've been staring at it, it actually looks like it's readable. There's a GPS reckoning system that if the sailboat goes off, this is a cruise ship I think they have, and this cruise ship goes past a certain point or gets lost or something like that, it offers a GPS rerouting, like an autopilot mode that should happen. And in this particular case study, in the analysis of what happened, the ship was steered by an autopilot that relied on a positioning information from a GPS system. And if the GPS couldn't obtain a position from the satellites, which in this particular case it couldn't, it provided an estimated position based on a dead reckoning distance from. Dead reckoning is the distance and the direction traveled from a known point. Only problem is the data was wrong. So it ended up going around in circles, and the system ended up failing, essentially. And the point was, how reliable was this? And the GPS failed 1 hour after leaving Bermuda. The crew failed to see. So there were people involved. They failed to see that the warning message on the display or to check the instruments. They didn't even know that they were in autopilot mode or they were in this dead reckoning kind of position. 34 hours and 600 miles later, they were only 17 miles. The dead reckoning was a 17-mile error. But essentially, they were just going around in circles for 34 hours. If I were a passenger on this boat, I'd be pretty upset eventually. So all the software worked as specified. There were no bugs, which brings up the concept because a lot of people think, what is reliable software? This doesn't have any bugs in it. It has nothing to do with testing. It has nothing to do with bugs. This is an example of what happened when the software, well, it was reliable in that it automatically went into this dead reckoning mode, and the GPS went into autopilot essentially, and it did what it was supposed to do. There weren't any bugs in the program either. Was it dependable? No, because they never made it to the destination. They couldn't depend on the ship to actually navigate them into the correct. They could rely upon it, but they didn't depend. It wasn't dependable, long story short, because it never made it to its final destination. It only made it 17 miles away from somewhere. Or it was off track completely. It was a complete waste of time. So since the GPS software had been specified, And this is what happened, actually, in terms of the errors. The requirements had changed. How often does that happen? All the time. So that's what happens. From Software Engineering 1, we learned that requirements always change. And that you start the project out from day 1. By the 2 years later, by the time, or a year and a half later, by the time you finish the project, the environment's completely different. So that's a given. So standalone systems standalone system to part the integration system. Maybe it needed one. Anyway, the manufacturers of it also adapted different design philosophies. The design philosophy itself, to use this dead reckoning thing, created a situation in which, it wasn't designed correctly. And the autopilot was not programmed to recognize valid and invalid bits as either, so how do you even know that it was even not getting a proper signal from the tower, and why did it even need to go into this mode? And the warnings provided the user interface, they weren't sufficient to actually alert the crew. Like there was no big red light or something. There was just these messages that were showing that were ignored. So the user interface for the crew to actually recognize this also failed. And they hadn't properly trained the people on the equipment. So this is like, finding someone to fly an airplane and not telling them about, or fly an airplane, drive a boat, or whatever, without telling them about all the features the system actually has, which is an issue as well. So it all kind of plays into the same concept of what this reliability. So here's some definitions. Reliability, probability of a failure occurring in operational mode. We have failures. Failures will occur in software. Software is not 100% science. It will happen. Failures will happen. But what happens when it does happen? Perceived reliability depends on user behavior, the sets of inputs, and the pain of the failure. Depending upon how bad the failure is, the perceived reliability score changes. It's like Windows. If it drops out completely and your whole computer shuts off, not very reliable. However, if it always is making a ton of errors in the background but you just don't know about them, reliable. Depends on the significance. So the user's perception of reliability, personal computer that crashes often versus a machine that is out of service for 2 days. So a lot of times reliability depends upon, how long does it take for the system to become available, which is why I talked about availability as one of the main points. The AWS system that crashes comes back quickly with no loss of data versus a system that fails once in 3 years and has to be restored from a backup. So these are user perceptions to think about. A system doesn't fail but has unpredictable periods when it runs very slowly. So you have design choices to make. And in fact, you see this happening a lot with network applications. It just slows down to nothing. Is that better than having it come back with an error message, no connectivity? I'd rather have it say no connectivity personally, but there's other people that wouldn't want to have it down, would want to have it up. So here's some metrics. So the traditional metrics that we might think of in terms of, and we think about this when we start looking at reliability plans and assessments, and this builds into risks as well. Yes?
It's like, according to me, what all I studied, dependability is like an umbrella, and the reliability, security, and availability, and one more feature. They both are like these 4 factors, make the system dependable.
Yeah.
When we say the system is dependable, reliability should always be there, I think.
Yeah.
So when we say the system,
rarely you'll have a dependable system that's not reliable. Usually they go hand in hand. It's just the terminology. The concepts are almost identical. It's the terminology that varies. Yes?
Is it vice versa for reliability and dependability?
Vice versa. You can have a pretty unreliable system that's dependable.
yes.
Because other features are mapped, like availability, security. Everything's are there.
The features aren't necessarily mapped to one or the other. It's not a vice versa. If they both work together on the same plane in terms of features of software. But they both actually mean 2 separate concepts.
So if a system is reliable, it has to be dependable.
You can have an extremely unreliable system that reboots itself every 5 minutes. because it crashes from errors completely. But because it reboots every 5 minutes, I can depend on it being available. It's kind of like people's cell phone service.
Yes.
It's unreliable. You don't necessarily know you're going to have a signal and you're going to make a call, but if it keeps resetting itself every 5 minutes and you can put in a new battery, you can make it dependable. You can depend on it if you need to make a call. Eventually, lo and behold, it might actually work for you. So the user's perception of the dependability is a different quality than the user's perception of the reliability of it.
It also depends on the redundancy, like how many.
Reliability would play into redundancy. To make something reliable, you want to make it so that, let's say, if this server isn't up, then this server is going to be mirrored with that server, so you can get at the data through one of the servers.
So
both of the servers are unreliable, but you can depend on getting the data. Huh?
So dependability depends on redundancy.
No, because you don't have to use redundancy for that. You could just say, instead of that, let's just say, if the server's not up, then because it's a power failure, then we have a battery backup. We don't have any redundancy, we just have we have a closet full of batteries that we've hooked up. We don't have any redundancy at this point. Instead, we're relying upon battery backup to make it reliable. And we can depend on, because we have all these battery backups to make the system reliable. We don't have to have redundancy for something to be reliable or dependable. And we don't have to have battery backups either. It depends on the combination of things that you're putting together that's going to give you the perception. And it's perception. It doesn't necessarily mean something actually is reliable or dependable. It's the user's perception. I mean, if I know that my car runs out of oil and I can't rely upon the engine because there's an oil leak, and I go to Costco and I buy cases of oil and I stick them in the trunk, I can depend on that car getting me from point A to point B if I have to pull over every 5 minutes to load more oil into the car. Not necessarily the best car, but it's dependable, unreliable, but dependable. So let's go back to some other ways in terms of relating it to software outside of cars. But sometimes you take it away from software. Software is hard to understand. It's hard to actually see that in software because in a car, it makes more sense. But software is so different, so it's hard to really think about it. Traditional measures, we have the mean time between failures, availability, uptime, mean time to repair. How long does it take to repair it? That makes it reliable or unreliable. If it takes too long, it's not reliable. Market measures, complaints. Complaints, actually, that's what happened to Windows Vista. So many complaints. The operating system wasn't really that bad. Compared to all the complaints it got, you'd think the whole entire operating was unreliable completely. Which, it wasn't really that bad. Customer retention, how long, are people switching off of the system? That would make, if I were a cell phone user, I'm actually already off AT&T, but if I was still on AT&T, I might think that the service is bad. So, I can't rely on it. And because of all the complaints of all the people who had iPhones who weren't happy with it. User perception is influenced by the distribution of failures. How many lost calls, dropped calls, problems, how slow was your service? That's a factor. So hypothetical example, cars are less safe than airplanes in accidents per hour, but safer in accidents per mile. Actually, the number one worst thing is the car. There are more automobile accidents than anything else, and the statistics show that cars are unreliable compared to airplanes. But when one flight goes down and kills 200 people automatically, it's not safe to fly. It's not safe to drive your car, actually. It's safer. Your odds of getting into an accident are higher in a car. But people think that cars are more as a more reliable, safe form of transportation versus flying. There's people who are afraid, even today there are people who are afraid to fly, but they're not afraid to drive a car. So, I don't know, go figure. It's backwards. All right, so reliability metrics for distributed systems. So here's just pointing out some of the difficulties. So software is okay. We can kind of understand it from a standalone. Let's distribute it out over a network. already increased the complexity. So the traditional metrics are hard to apply to multi-component systems. What do we have today? Everything's multi-component, which is why it makes it more difficult, long story short. So in the big network, given moment, something might be having problems. It might be a server. It might be a connection. It might be a virus. There's so many. It might be overload. It might be, maybe a lack of load balancing. So we increase the complexity. Excellent average reliability may give terrible service to certain users. In that case, you would have a system that was extremely reliable yet undependable, because some users may not be able to connect at all. However, as a network, it's up completely, 24 hours a day, 7 days a week. It's just the service quality is not so good. Maybe not available to everybody. So it's kind of like, well, it works for everybody, but 1 out of 10 people are going to have a problem with it. If you're the 1 out of 10, you as a user, you're not going to think that that system's dependable. So many components, administrators rely on automatic reporting to identify problems that arise, and then if the automatic reporting is not good, then the whole thing might be hosed as well. For an ATM card reader, as an example, you can come out with some reliability measurements. One of the assignments, I believe it was the second or the third assignment, talked about reliability. Was that risk assessment? I don't know. The second one was a reliability plan. So this is really where we dropped off. And I think didn't I cover reliability last?
Yeah, you did.
I covered this already? Okay. No?
Not everything, but...
Okay, maybe, I don't know if I covered this lecture or not. Maybe I covered just the first part of it. Cost of the reliability. Uptime versus money. I think I actually may have covered part of this already.
Yes.
Yeah. So I'm going to kind of skip through it because it's hard to pick up where I left off after several weeks or several months. So you'll spend your money on new functionality or improved reliability. That's a cost. Are you going to add more features? Because you're a software development company, you're putting out new software packages. Are you going to waste your time on reliability? It depends on your bottom line. In terms of the central computing system, and these are just some case study, and this is what I mean by case study examples. Taking a look at a company, looking at the statistics. So when I say, here's an example. Central computer serves the entire organization. Any failure is very serious. These are some steps that they would go through to make the system reliable. Gather data on every failure, analyze the data, and then I believe I actually have covered portions of this lecture, so I'm going to skip through quickly and get to the next one. Invest resources where benefits will be maximized, hopefully, and then implement a plan. So we have building dependable systems. So let's talk about dependability for a second. 3 principles of dependability in terms of building it. So for each software system, for a software system to be dependable. And now we're looking at the development, we're looking at testing. So each stage of development must be done well. So the development process should be done. This is why we follow software engineering methodologies, so we can build dependable systems that we're going to have dependable results. Changes should be incorporated into the structures carefully as the original system was developed. So we take the same amount of effort in terms of our maintenance as we do in terms of our development. Testing and correction do not ensure quality, but dependability systems are not possible without systematic testing. This is where we get regression testing. Regression testing is done so we can have dependable systems. We can depend that the upgrade, the maintenance, the features that we've implemented aren't going to ruin the system, and when we have peace of mind when we put that software back onto the market, that we haven't introduced any problems. And here's how the changes play into effect. So reliability with the modified water model, we're building it into each one of the stages. In terms of how the key factors of dependability and reliability work with software development models, it's very hard to put it in the waterfall model. It's easier to put it in a spiral model, but not necessarily. Incremental development, the best. That was another midterm question. Uh-oh. I'm not giving that answer away, though, because the question's worded differently. Anyway, I hope someone's taking it. Oh, I totally forgot. Maybe she's not listening. Okay, that's good. Alright, so alright, let's move on to that one because I don't want to beat that one up. Key factors for reliability software. And just, actually going back to that last point I was making, think about software development models, what's happening in terms of the development. If we're producing a product using the waterfall model, what ends up happening, we start day one, we go through feasibility requirements. Everybody knows this waterfall goes downhill. So we start, at the end, we don't produce anything until a month, well, until a year, 2 years later. Hard to implement changes, hard to implement problems. If we put out prototypes, if we put out incremental development, then we actually have the ability to quickly react and to quickly change. We build more reliable systems that way, which is why a lot of people think reliability is sort of an afterthought. It's kind of like testing is an afterthought with the waterfall model in a lot of different ways. So key factors. The organizational culture that expects quality. The approach to software design hides complexity. So we're using abstraction, we're hiding the complexity, and might actually gives us the harder playing ground to work with in terms of reliability. We might have precise, unambiguous specifications, hopefully, which is going to help us in terms of lowering or raising the expectation, lowering the problems. Using software tools, programming style, and incremental validation. Validating things incrementally is going to help you as well. And good organizations create good systems. So building in terms of the organizational culture, and this is actually something you have to build in. It's not one of these software qualities, reliability, actually it's not something that happens naturally in the development. It's not something you can build in as a feature normally, which is why it's usually an organizational culture or it's a way of thinking in terms of the development staff. And you bring it in mostly when people are aware of it and you've discussed it among the group so that someone can say, you know what, shouldn't we have a backup? Shouldn't we log all this stuff so just in case the system crashes, the customer doesn't have to go through the entire transaction over again. We can just bring it up at the last page where they left off and stuff like that. So these comments come out as features that are implemented as a culture actually or as a way of thinking. So. Visibility, completion of tasks before moving to the next is also good. Human mind can encompass only limited complexities, comprehensible, simplicity, partitioning, so making the problem easier, taking the big problem, breaking it out. So simple system or subsystem is easier to get right than the complex one. So solving all the little problems and then putting all the little problems together to solve the big one is good. And then in terms of specifications for the clients, looking at specifications are no value if they don't meet the client's need. So if you built the best system in the world and you have really bad validation and you haven't actually met all the customer satisfaction, the system's not dependable. They can't use that accounting system. It becomes very undependable. It might be an extremely reliable system. It might do what it's doing quite well, but it's not doing what the customer actually wants, which would give it a low dependability quality, but a high reliability. So dependability, you might think, actually goes way above and beyond the design of the software or its software qualities, and it may also, might be a quality that's user-related. And you think, well, that has nothing to do with software. It does. Users gave you a list of requirements. If you didn't implement all those requirements, you haven't built a dependable system. So you can think of it in that perspective as well. So it's kind of like validation, verification. It might not be a valid solution to the problem. It might verify out correctly. So if you don't know, there's a difference between validation and verification as well. Kind of like the differences between reliability and dependability in some ways, actually. Very similar in terms of the way it's perceived by the terminology. And it is terminology, but it's more, there's a concept behind it as well to kind of consider. All right, so the clients must understand and review the requirements. Appropriate members of the staff must review the design. The acceptance tests must belong to the client, so the client can actually go back and review through that. We have some assumptions. Good processes lead to good software, hopefully. Important in the routine, standard terminology, using software standards, reporting techniques, and stuff like that. Using change management. I talked about this in software engineering once. I'm going to kind of skip through it, but this is where the change management, release control, things of that nature come into play as well. In terms of the plan, objectives: review the progress against the plan. Make sure you're actually on plan. Makes no sense to come up with a development plan, strategy, risk assessment, anything, unless you're going to actually see if you've made it, see if you followed it. The impact on quality results in making demands realistic in the future, making better plans. So, I'm not quite sure what the whistling is all about. In terms of reviews for the design and the code, design and code reviews are a fundamental part of software development process in terms of having people look at it. This is where testing, benchmarking, software reviews come into play. Also an important concept because you can find things and you can communicate and you can improve. Oh, those people have taken the midterm. Again, another question that was actually kind of a key component, and it is also covered. Since called a midterm, it's a final, I guess. The concept of what we're trying to accomplish with a software review is different from the concept that you're trying to accomplish with testing and with other forms of that software validation, verification. And the review is sometimes nothing more than a form of communication, and also to increase morale among the development team. And it serves different purposes. It actually works more with validation as well. Dependability and reliability play a part in that as well. Benefits of the design and code review process: benefits: extra eyes, spots mistakes, maybe suggest improvements. Colleagues share experience, training. In fact, then you get that learned knowledge, learn corporate stuff. On occasions, you might be able to tidy up some loose ends. Fundamental requirements: senior members must show leadership. They must actually want to participate in it. Reviews don't make any sense at all if the people don't want to share, don't want to. And it's really hard to get programmer-type people to be communicators as well. Good reviews require good preparation. Everybody must be helpful, not threatening. It's not like criticizing. So a lot of review processes. Is there something like something just end, like a soccer game? Just kidding. Cricket? Just kidding. Yes.
Reviews come as a verification.
It is a form of validation. Yeah. Verify. We verify software to make sure that we have implemented all of the features of the requirements. We validate it to make sure that we've got a valid solution to the problem.
So, testing
And we
falls
have
under
reliability.
validation.
Huh?
Testing falls under validation too.
Testing is more verification. We verify that the features are implemented correctly and that the system is bug-free and that we have... So we verify to see if we have implemented all of the requirements. We validate to see if the requirements were correct. Always think, is this a valid solution to the problem? Have we verified that it works?
So generally, whenever the product is created, after that the testing is done. Generally,
Testing happens theoretically throughout the life of the development process. Most people inexperienced in it would wait until the very last. The product is finished, then they decide to test it.
But only after a module is completed can the testing be done on that module.
Correct.
So once it's done, we validate whether that product has been built correctly.
You verify whether or not that particular module.
As per the things we have been studying, it's like more of the documentary things, or say reviews, inspections, all that come under the verification.
Verification, yes.
Yeah, and when they say validation, I mean they equate, the validation to the
It's a commonly misused word. It's kind of like how everybody calls everything object-oriented or engineer. You verify the existence of a bug. You verify a fix. You verify a module is complete. You validate to make sure your solution is correct. It's a valid solution. It's a valid accomplishment. It's a valid component. Verify, validate. People mix the terms up constantly. They interchange the terms constantly. Technically, they're both getting at the same concept. Did you build it right? But it's one of them's did you build it right, the other one's did you build the right product. According to, tradition and software methodologies. Textbooks will always say validate is it the right answer to the problem? Verify, does it work? So when you get verified, how do you verify a user? You make sure that the user's in that login name is correct and that their password's correct. And if they're a valid user, which means they've gone through the verification process and now they're validated, then you give them access to features of the software that valid users have access to. You can think of it that way. I don't know. Most people would come up with, for me personally, did I implement all of the requirements? Can I verify that the requirements are implemented? And is this a valid solution to the problem? That's how I remember it. But you guys might have your own saying, or you might have your own way of conceptualizing it. And you'll see everyone saying, can you validate that? And really what they mean is, can you verify that? How can you validate that without verifying it? You got to verify it first, then you can validate it. So it's a play on words for a lot of people, actually.
So verification will say it's a set of activities and validation is a part of verification. Can you say it like that?
Yeah. Validation is a part of verification, yes. Verify that this works and it's implemented correctly. Because you can have something that works just fine. It's verified. I've implemented all these features. I gave you what you asked for. But it's not a valid solution to the problem. It's an accounting program. I wanted a human resource program. Yeah, it's great. It works. It's verified completely. But it's the wrong system. It's not a valid solution to my problem. I can't validate this. Just like the student who's verified that they have taken this class, they have verified that they've taken that class, and they've verified that they've taken this class. You add all these classes together, do they get their degree? No. Because they didn't take they didn't follow the valid program structure. Valid, which would be correct. Verify is usually correct as well, which is kind of where the confusion comes into play, I think, is why people switch those words around a lot. But there is a true meaning for it, just the same way there's reliability and dependability. But you could spend all day trying to figure out the differences between the two concepts and which is more important. Neither one of them is more important than the other one. They're both they're qualities of software, just like reliability and dependability is a software quality. So fundamental requirements, senior team members. Oh yeah, I'm sure review. Okay. Review team, full version. If you have a moderator, subscribe. Developers, interested parties, outside people. You can bring in almost everybody to do reviews on something. In fact, you can mix it in with part of your acceptance testing. Actually, in fact, a lot of people do that. In fact, you have a software package you built, your Acme software development. You build an accounting program for a company. You can do what they call a walkthrough or a system inspection. And what ends up happening is you show it to the customer, you show it to developers, you run through every one of the features. And I can take that back now. I'm talking about all this. It's on this exam. Let me get this exam back. That's such a great idea, Jess. Thank you. Thank you. No problem. And at one point, you're helping the development team as a review process. You're helping the customer understand what was implemented. You're facilitating part of the testing at the same time as well. It's a form of testing. Walkthroughs, inspections are testing. Actually, in fact, you put that in your test plan. And then you can lead that into it. And if it's in the test plan, it's part of the acceptance testing. And then you can lead it into further documentation to help the next software development project go a lot better. So you can learn from it as well.
But the walkthrough and inspection are done for code reviews also, like in the development process also.
That's more of a desk inspection or walkthrough. Again, the terminology is often used in different ways. You can do it from a code level, where you're going through each line of code or each module. You can do it from an implementation. This is how you do it. You can do it from a user's perspective, user interface perspective. If you're doing it that way, you're probably doing it for acceptance testing. Look, here's your accounting program. This is how you make an entry. This is how you do this. And the customer's coming back and saying, but how do I do HR with this? You're verifying and validating that everything is implemented and that everything is working, and then this is how you use the features would be the walkthrough part of it. It's not like, when we've done building your house and they do a walkthrough, walk you through each one of the rooms. And look, see, there's the windows you wanted. There's the door. All the features that you requested. So it's made as a final inspection / validation. What I got here? Preparation meetings and things of that nature. Static and dynamic here we go. Here's some verification. Static verification versus dynamic verification. The statics are the techniques for verification that do not include execution of the software because it's not running. It's just like a static still. Maybe manual, might use computer tools. Dynamic is going to be testing the software with trial data, debugging to remove the errors, maybe that nature. So, and here's how we get the static validation and verification mixed in. And you'll often see it together. Validation and verification are together. You'll see it together because it's done together. You can't have one without the other. You could have one without the other, but both terms end up together in the same category of a quality that you're looking for in the software. So we have requirements, design, program. We have reviews that aim, and the focus of the reviews are to validate and verify, essentially, which is what that is supposed to be meaning. Program inspections, these are some examples of things that might happen. Formal reviews show objectives. So defect faults, code may be read or reviewed line by line, may not be, might be done in modules. You might use a checklist for common errors. In fact, that's what you would actually do when, let's say, you're going to fly a plane. Usually there's a checklist. Check the gauges. People actually did this with cars when they first learned how to drive. Check the mirrors. Make sure the seat's in the right position. Is my coffee in the right cup holder? And you go through all this little thing, and then, okay, I'm good. Turn the engine on. Look both ways before you pull out of the driveway. Now people don't forget. People don't do that. But it's a process. So it's the same thing. You do it with software. Did we print out? Was the user logged in first? Okay, good. To make sure that they have proper features. So inspection list, common errors, default errors, control faults, input-output faults. These are all parts of things. And if you're looking for ideas, this lecture is great for the test plan. You're looking for ideas about how to validate and verify. It's not going to go through a bunch of testing, but it's going to go through analysis. So, static analysis tool, program and analyzers can analyze the data flow, the control flow, interfaces, faults like that. Static analyzers in terms of the tools themselves, show the use of every variable, procedure, objects, components, identify the information flow, the inputs and the outputs, and do the cross-validation, verification. Let's talk about failures and faults for a second. They're actually, similar. A failure, software does not deliver the service expected by the user. It fails to meet the user's expectations. Just going back again, if you didn't like the differences between validation and verification, you're not going to like this terminology either. Mistake is requirements confusing the user interface. Maybe a fault is a bug. So a failure is this software is not delivering what it was supposed to deliver. So failure is kind of like it's not valid. And this is not verified. There's a bug. We can't verify that the feature is working correctly because there's a fault. Faults are bugs. Faults are not failures. Excuse me. Bugs are not failures. If it has a bug, it has a fault. If it's missing a feature, it has a failure. Okay, so it doesn't conform to specification, doesn't work, there's an error in the system. Actual examples of faults and failures. Mathematical function loops for every rounding error. You can come up with your own. Everyone who's ever written a program before has probably figured out that bugs exist. And there's many different forms of bugs that come in all different shapes and sizes. Failures. Terminology, we have fault avoidance. Oh, also on another thing that's going to be covered on the final as well. Fault avoidance, fault tolerance, and fault detection. Fault detection works with testing and validation. So let's see, fault avoidance is you build systems with the objective of creating fault-free, bug-free software. So you're avoiding introduction of it by following methodologies, practices, standard routines. Tolerance, you continue to operate. Will this system go down or can it tolerate a bug? Can it tolerate a bad password 5 times? Or can it tolerate a lack of an internet connection when it thinks it's supposed to get an internet connection? Which means you're building features into the software because you know there's going to be problems and bugs, and it's going to recover from those particular problems and scenarios when they happen. Bug detection, can you find them? Can you detect the bugs before the system is put into operation? Used in testing, also used in validation. And you could probably add verification in there as well. But we're not normally verifying at this point. It's premeditated. It's pre-verification because at this point we're just trying to find the bugs. It's just more testing. So, and then I'm thinking, well, how does testing work with verification? Almost the same word. When you test something, you're trying to verify if it's working correctly. So it's really, you can substitute testing with verification if you wanted to, in terms of the concept. Yep, I got it coming up. I got each one of them. Huh? Example of which one?
Fault avoidance.
Fault avoidance?
How do
You avoid faults by making sure that the system isn't going to load unless the file is there. Like, you can't open up a file unless it finds the file. You avoid the situation in which a fault is going to occur. So you can't save a file unless you've got a file open.
putting it in?
Yep. Building the features. Fault avoidance is in your feature selection. Putting in options, putting in features, putting in a default. If none of the other ones were selected, then this last one will be selected automatically for you. Initializing variables to 0. Just in case the customer doesn't enter in a number, we have 0 instead of null pointer errors or something that might come out of that. Initializing variables, actually, that's a good point. If you're a programmer, you probably could relate to that one. Because otherwise you're going to end up with bugs. Look, it comes out, not a number. Oh, jeez. My whole mathematical calculation fails because I didn't initialize it to 0. Fault avoidance. Formal specifications. Here's some other examples of the software development concept. Incremental development with customer input helps you avoid problems, especially when you're showing the customer and you've incrementally developed it. Constraining programming options, limiting yourself. I'm only going to use object orientation. I'm only going to use a static verification, statistical testing, finding out, an example might here, the 4-color problem. Well, I'm not going to go into that. It's better to prevent defects than to remove them later. So you might think avoidance is avoiding the introduction. Defensive programming, Murphy's laws, if anything can go wrong, it will. So in terms of defensive programming as a software engineering methodology, actually is redundant code is incorporated to make sure that states different modification testing programs. This is what unit testing is defensive programming. So some of you may be familiar with the software engineering one, the J units. I think I covered that actually in that course. I actually covered it in the Android course too if you took that. Where you're building a test case to go along with the class that you're building. You're practically doing twice the level of programming. But you have the ability to defensively go through and test each one of the methods, each one of the classes, make sure that the proper input and the proper output is received. So it doesn't matter how the class is used in the real world, it works, essentially. So doing that, implementing assumptions are tested explicitly. Risky programming constraints are avoided, not using pointers. Some people might think that's a defensive mechanism. It's kind of like how human beings can defensively do healthcare management. If you don't smoke, don't drink, don't drive cars, don't fly in airplanes, don't live, essentially, your chances of living longer are a lot higher. Although the cost of living, I don't know, you could probably, that's another philosophy, in terms of how you're going to live life. You're not ever gonna have a problem if you never drive a car or fly a plane. You see half the world, but you're not gonna die in a plane crash if you don't get on a plane. That's defensive. In terms
What
of
if a plane crashes on
without the people, if you wear a parachute in your plane, that's defensive. That's defensive passengers. I know. All right, risky programming constructs, pointers. You probably go through, depending upon the programming language that you're using. There's things that you can avoid. In fact, that's an excuse for a lot of C++ programmers never to touch pointers because it's risky. You can make a lot of errors. Okay. Maintenance. Doing software maintenance is a defensive technique, actually. Most production programs are maintained by people other than programmers who originally wrote the code, which is why software decays. It eventually becomes unusable. What factors make programs easy? By somebody else to maintain, putting in comments in the code. That's defensive programming for maintenance purposes. Documenting things. What factors make a program hard for somebody else to maintain? Thinking about that. In terms of the fault tolerance, failure detection, damage assessment, fault recovery, fault repair, issues that might actually come up in terms of your figuring out how you're going to design your test plan, right? Because you want to find errors. Well, what kind of errors can you get? Usability errors, programming errors, design errors, network errors, so many different types of errors. So you're going to test for just one type? No, you're probably going to develop the test plan that tests full coverage of all different types of errors that might actually exist. In terms of fault tolerance, the basic technique after an error continues, will the next transaction continue? Will it drop a packet? Timers, timeouts? Let's say we have an error. Let's say the network is going to go down and our program needs the internet. Then, in terms of fault tolerance, we can figure out, how can we reduce the number of times that it has a dramatic effect and we only use the internet. Actually that would be, fault avoidance would be only have the program look for that connection when it really needs it. So just in case the connection goes away, some of the other features actually might work. We can avoid faults. Fault tolerance is figuring out how are we going to repair the error? How are we going to figure out, assess what's going on in terms of, are we going to be able to continue? Or going to put in, how long are we going to wait for that particular screen before the program determines that we don't have an internet connection yet? It helps with the usability. It makes the system seem more reliable if it comes back instantly. Hey, we don't have a network connection. Would you like to try this later? You can move on. You can do another transaction at the same time. And then we might get the connection back. Who knows, 5 minutes from now or something. The program's never going to tell you that, but that's what it's going to do in terms of tolerance. Timers, timeouts, error correcting, bad data blocks on disks, fixing problems. Recovery, actually, so that the system, you don't lose your data. So record backward recovery, checkpoints, doing a commit, doing a rollback. Thinking about a transaction, so not all of, let's say, if part of it doesn't work correctly, the whole thing doesn't work, so we can roll back, we can fix problems. Software engineering for real-time systems, a little bit different as well, where we have requirements analysis, design of the tools, modular design. So special characteristics for real-time computing require extra attention to good software engineering principles because we have to make the thing pretty solid. We can't have cutting-edge, bleeding-edge software programs out there that are working in a real-time environment that are not known, not tested well, that don't recover well from errors. I mean, it's like if our traffic controller falls asleep, a recent problem, our whole system goes down in a real-time environment because when the plane operator, airplane pilot tries to contact the tower and the guy's asleep, he's not going to get through. So what do? We do fault avoidance. We hire 2 instead of 1 now. So the other one, hopefully they both won't fall asleep in the future. But if one of them falls asleep, the other one can wake them up. Maybe we have, it's kind of like how we have, I shouldn't say that, it's kind of like how IT hires TAs. Or maybe it's how we send out email messages. I don't know. Good, bad. bad line of jokes. It gets frustrating after a while, though. That's where the jokes are coming from. All right. We'll just send out a dozen messages with all different due dates for everything. That way we might get one of them right. Okay, testing. Let me focus back here on something positive. Testing and debugging. Need special tools and environments for real-time systems, live, active debuggers. Just as distributed systems pose problems for reliability and for dependability and things of that nature, for testing in general, so do real-time systems. They pose even a completely different set of problems, but they do present themselves. So you can't be treated the same way. You have to treat the environment differently. Some notable bugs. Yeah, okay, so that was everything you ever wanted to know about software reliability. This is Lecture 6A. I do highly recommend that you take some time, go over it in a lot more detail than that. In fact, to answer some preliminary questions about, let's say, the final exam or things of that nature, if the best preparation would actually be to go through and read the slides. Actually, because I haven't really assigned a textbook for this course, so downloading and reading through the slides is a great way of absorbing a lot more, because there's a lot of writing on the slides, and I'm not covering all of it. I'm just giving you the main points. So. Are we good to go a little bit longer, a half hour longer? Then we'll take a lunch break. I can probably get through another lecture or two. All right.
Can we have a roster?
I'm sorry. Oh yes, the roster is going around. In fact, those of you who came in late, I don't know if my TA is still here. There's some room on the back of that one. Make sure you do sign it, because I know some of you aren't going to come back after lunch. So. And just in case I forget to say it, if for those of you who aren't coming back after lunch, we're not meeting tomorrow. It's just today. We just meet on Saturdays. And if you're brand new, and this is the first time, this is how the last session went as well. And if you're really brand new and you missed the beginning, and this is the first time you've been here, check the final exam schedule. It does run on Saturday and Sunday, April 30th and May 1st. All right, so what is this? This is the next part of it. And believe it or not, I've actually kind of covered this lecture as well at the same time, because I talked about dependability. This lecture is on software security and dependability. And not to confuse you even more. We always think about security and dependability all in one. Because secure systems make dependable systems. Insecure systems are not very dependable. So I have to talk about what makes software secure, and security as a quality, and dependability. So I kill two birds with one stone and then reinforce the concept of dependability and bring it right around with reliability, because it all works together. So dependability properties, the system attributes that lead to dependability, is going to be covered. Availability and reliability. So if you want to memorize it that way, you're going to say reliable systems and available systems usually play hand in hand. And also with dependable systems. Safety, what does it mean to be safety and security? All right, so system dependability. All right, so software and system. Software, we all know what software is. Some of us don't know what systems are. They always think a system is a software. We have system engineering and we have software engineering. You are sitting in a software engineering class. It would be different if this class were called systems engineering or systems. Actually, it's usually referred to as systems engineering and not software development. There's no system development. Why there's no system? Well, there's system development, but you don't ever see that as a title. So a system is this software package, that software package, that software package, that software package. All put together to give you the system. Software, software 1, software 2, software. You could have, not to confuse you could have software that's distributed that all runs in the same software system. Java, as an example, RMI applications. Where you have software and it's a software system, it's a middleware application. It's running on many different software that's running on many different systems that's all the same software. That's the newest, more modern approach. The traditional approach is software only ran on one system. It only ran we defined the system instead of defining the software. Now we can actually do it interchangeably. Not to confuse you even more, the difference between software and system. Think system is the big picture, which is how we can have dependable systems or undependable systems, depending upon the underlying software and the different software systems. We might have one software system that is not reliable. We might have one that is reliable. Can we depend on the entire system working correctly is more of a dependability issue versus a reliability issue in terms of the way that the terms are actually used. So for many computer-based systems, the most important feature, property is the dependability of the system. I would say so. You know, when I shop for software, I don't care, you know, as long as my operating system works. If I can depend, when I press the start button or whatever, when I press the power, it comes up. That's probably the most important feature for me. And also, you know, in terms of dependability, can I find the features that I want? Can I use it can I use my operating system as a calculator, as a PowerPoint presentator, as a Word document viewer? So dependability of the system reflects the user's degree. Again, it's the user's trust in the system. You might relate it more to trust versus liking. Reliability is, do they like it? Are they offended by the system because it crashes every 5 minutes? Dependability, you always think of it, I trust it. It's dependable. It's my old pen. You know, when I take my exam, I want my pen that's dependable because halfway through the exam, I don't want them to run out of ink or something. I want to make sure I can write correctly or something. So it reflects the extent of the user's confidence, that it will operate as the user expects, and that it will not fail in normal use. It can fail anytime it wants when you're not using it. That might make it unreliable to some people. So dependable covers the related systems, attributes, reliability, availability, and security. So dependability also covers reliability. It's a blanket term, also covers availability and security. Interdependent. They're all interdependent. So if you remember anything, if you're totally confused by the time you leave today, if you remember anything, just these are all interrelated terms that all mean pretty much the same thing, bottom line. But they're all used differently, and it's a vocab test is what this is. The importance of dependability, well, we know about reliability. If it's not reliable, people aren't going to use it. It can't be part of the system. It's not going to work. It's not reliable, but replace it with something else. If it were hardware, it would be replaced immediately. If software, it would be fixed constantly over and over again. The importance of dependability, system failures may have a widespread effect with large numbers of people affected by the failure. Do we want to affect, if the network goes down and people can't use their AT&T cell phone service when they really want to, people are going to leave AT&T. They're going to go to other carriers. That's a known fact that's happening right now. Systems are not dependable and are unreliable or unsafe. They might be unsafe or insecure. Oh, now we're playing the news. They may be rejected by their users. Obviously, if they're not secure, then you're not going to use it. If your program, if you're operating, well, this is not true. People use Windows still. Windows, well, now they add antivirus software to it, but theoretically, it's not as secure as, let's say, the Mac system. But people would use it anyway because they don't like the Mac for some reason. So people will use Windows even though they have to load on 20 different antivirus, anti-spam, anti-everything on it because it's not secure. As an operating system, it's very insecure. So they have to rely upon third-party programs to make the operating system secure. But they can rely on those programs.
So why can't Microsoft work on it?
Very good question, and if this were an operating system class, I would go off on that.
Just like Apple.
You want to know why? Because hackers don't spend enough time trying to break into the Apple system. They'd rather spend it against Microsoft. Well, you see I'm using a Mac. I am not a fan of the Microsoft. You don't even want to get me started on that one. And we'll never get to lunch. I skipped that one. The cost of the failure of the system may be very high if the failure leads to economic losses and physical damage. Oh, let's talk about a bridge that opens and doesn't shut. That might be an issue. People might sue because they lost their job interview or their car got damaged. Oh, paint. That's a good thing. You know, those paint things. Actually, it's about 5 years ago. I think it was Toyota. Put a clear coat so your paint wouldn't the sun wasn't going to what do they call that? Oxidize the paint. So they put a clear coat. Instead, the paint chipped off. So, undependable systems can cause information loss with high consequences. Yeah, you won't want to use an undependable system on your ATM, and then all of a sudden the bank doesn't know how much everyone has in their accounts, or has the wrong amount in your accounts. You can't depend upon it correctly. Cost of a failure, hardware or software operational failure. I don't have to get into this, I hope. This is what you can read at home. Principles of dependability properties. So this is more important. It's actually kind of blurry, it looks like, but dependability, we have underneath it availability, reliability, safety, and security. And usually when you study software engineering as a degree, you usually take a class in security. You usually take a class in testing for reliability, and that's where that falls into play, or for safety or something. You know, these are all different sub-areas that lead into the basic principles. In terms of properties, you can read through definitions on your own, I believe. On each one of them, most of you probably already know. And define these terms. Availability never gives anybody any problems. So, reliability could be a source. Safety, what does it mean to be safe? The judgment of how likely it is that the system will cause damage to people in its environments. Is it safe? Usually people think about health-related issues. However, it doesn't always 100% mean it's a health-related thing in terms of safety. I mean, it's going to cause injury. People think about it. Well, safety actually might think, am I going to lose my data? It has nothing to do with your personal safety. However, it's the safety of your assets. Your safe. If I put my money in the bank, is it going to be safe versus in a CD, or a stock market investment or something? Doesn't always mean health. Security as well doesn't always mean health as well. It might be, loss of data, loss of access rights. Repairability, maintainability, survivability, error tolerance. Again, more dependable properties. Not as commonly discussed. Maintainability, though, kind of gives you a good, solid, dependable feature that's not a reliable feature. You can have reliable software that's not maintainable. Everything's hard-coded. All the IP, everything, the whole thing is written in Greek. All the comments are written in Spanish. Yeah, not maintainable, but very reliable. Perhaps, maybe, hopefully it is, because you can't maintain it. Survivability, again. Is it going to be an outdated package? May be extremely reliable, but it doesn't survive the year 2000. So it's not dependable anymore. So all the bug fixes we did for the year 2000 were dependability-related characteristics. They had nothing to do with reliability. Actually, it dealt with survivability, the ability of the system to be able to be used past the year 2000. Fault tolerance also plays a part in there as well. But fault tolerance deals with reliability as well. Reliability. So some of the features and characteristics, as you hopefully can see, overlap. Some are part of reliability and dependability. Some apply just to one or the other. So that's why there's two different terms. That's why there's two different definitions of those particular terms. Same thing actually can be said for verification and validation as well. The rest of the slide set kind of goes through each one of these. So you can read this on your own. Repairability, maintainability, survivability, fault tolerance. So that's, yes, I'm sorry.
As a QA person, how would I go about ensuring or testing?
Did you say QA?
Yeah,
quality assurance? You realize you don't work in testing.
Yeah, what I'm saying. Testing. As a tester or a QA person, how would I go about ensuring the dependability of any software?
It's not an issue for QA or testing.
Ensuring, verifying.
Dependability is more long-term thinking. It's more planning. It's more of the development of the underlying concepts that are involved in the system. It's making design features that will build for dependability. As an example, going back to what I said about hard coding IP addresses, making it everything so it loads from a file instead of loading from the program itself. So you don't have to recompile the source code every time you change an IP address, as an example. It's a really bad example because nobody would ever do this. But it lends itself okay for this explanation. In testing, you'd never find that problem. QA, you'd never find that problem.
I was thinking of a certain testing.
What does testing do?
Verifying
Finds bugs in programs.
So,
Faults.
So like functionality integration. Is there enough for ensuring dependability?
No. It doesn't even start. It has nothing. It doesn't even address dependability. Dependability is not really addressed by proper testing or QA. QA and testing are more fault tolerance, more getting rid of bugs. It works more with reliability. In fact, I would put it in the reliability category. It has no mention and no concept dealing with dependability at all.
If you talk about a bigger, as a software consultant.
As a software what?
Consultant.
Consultant, yeah.
So how would you go about
The design of the system is going to be the earlier, so before the system is even built, you've got considerations for dependability. It's going to be more in the design, long-term planning, strategic developments. If you've got a system that is cross-platform compatible, it's going to make it more years in the life cycle than something that's built for one particular platform. It would make it more dependable. But my point was you can't, all the QA, all the testing, isn't going to fix that cross-platform compatibility issue.
That is more into finding the bugs and software.
Yeah. Reliability is more like, you're right. Actually, that's a good way of discussing it because it's more along the lines of finding the bugs, finding the problems, dealing with software-related issues in terms of the development. Dependability is more along the lines of the process, looking into a mirror ball and seeing in the future that some TCP/IP might go away or something, or seeing, I know it's not going to go away, don't worry about it, or looking at IP6 and you're currently in IP4, what happens if the IP protocols change? This program's not going to be dependable anymore. It's not going to work or something. It's more a quality, it's more features of software, actually. Think about it.
So basically it's planning.
Planning, development, feature selection. You actually have to build dependability in as a requirement. You actually have to build reliability in as a requirement. Going back to the concept of that and requirement specification, you can say right in your requirement specification it must be 99.9% reliable. Nothing is 100% reliable. 98 reliability. You're going to put a reliability and safety spec in the requirements for something that is something like a heart monitor or something. It must not cause damage. It must not, it can't have electrical signals past a certain voltage. It cannot, because that would actually injure something. Or it can't fail more than once every hour or something. It would be a reliability specification. A dependability feature is the battery's got to be replaceable or rechargeable because the thing's got to run constantly. We just can't open the person up, take the thing out, change the battery, and put it back in. How are you going to deal with a battery in a heart monitor? Or maybe it has to have a battery that lasts 10 years. That would be a dependable feature that you'd build into so every 10 years the patient went in and got it replaced.
More like, day-to-day functionality.
Yeah. Dependability, you can think of it more like the user's ability to rely upon it day to day. That's a good example. So I use dependability and reliability in the same sentence. No problem. No, actually it was a good tangent because It actually kind of reinforces what I'm trying to tell you. Dependability attributes, dependencies. Say that 10 times. Dependability attribute dependencies. Safe systems operations depend on systems being available and operating reliably. A system may be unreliable because its data has been corrupted by an external attack or something. These are just examples. Denial of service on the system tend to make it unavailable. So this kind of hopefully reinforces some of the points. The achievements: avoid the introduction of accidental errors, do some regression testing, which is why I mentioned before, regression testing lends itself to higher dependability factors, features. Design V&V verification and validation processes that affect the discovery of residual errors in the system, hopefully, ones that have been around there forever. In fact, there's software systems out there that have errors, bugs that have been around for centuries. Yep, so the BlackBerry has bugs, the phone, and it's still great. Why? Because it's dependable. The service is actually not bad. I mean, the BlackBerries themselves, they always reboot themselves nicely. They never crash. My Android phone crashes like every week. I have to reboot that thing. Twice a day. Yours crashes twice a day. Oh, your BlackBerry crashes twice a day. My Google phone does. It might be your network then. Did you know that BlackBerry RIMs had errors in that sucker? Residual errors that have been around since the first version of that OS that came out. That it will continue to be there forever.
Android is still bad.
You think you like? I don't know. I'm an Android user. I'm going to go back to it. I can't decide if I want a BlackBerry or an iPhone. But, see, now that everyone's leaving AT&T, the network's not as congested anymore, and they have the older version, the third generation, for $49.95.
AT&T just, they were about to make a deal with T-Mobile.
Oh, really? I think they should.
Yeah.
All right, include recovery mechanisms to help restore manual operations of the systems. Actually, just having a backup plan is good. There's cost. There are two reasons for cost. So dependability costs tend to increase exponentially as the increasing levels of dependency are required. It's just like maintenance costs. You know, if you want your car to be dependable, you actually have to take it and get the oil changed on it. You might not need it, but it needs it in the long run. So it's like preventative medicine, all these things. So the use of more expensive development techniques, hardware, require the achievement of higher levels of dependability. Especially the newer the hardware, the more things you have to put in just because the hardware doesn't work correctly or is not compatible. Increased testing and system validation are required to convince the system client, regulators, everybody that the thing is dependable. So the more cutting edge you have in your technology, the more you have to convince people. Not so much now than in the beginning. Now people are more are easy adapted to newer techniques, newer technology. As an example, the whole cell phone concept. People kept their landlines for years because, cell phones aren't dependable. Now people don't even have landlines anymore. They live solely on a cell phone. They don't have... And the landline, I said that to an undergraduate class over at Menlo College. I said, landline. They're like, what's a landline? It's like, it's a phone. It's connected to the wall. It's hardwired. Wait, you don't bring it with you? No, it stays at home. That's why it was called a home phone. Then we had work phones, and then we had cell phones. Now we just have a phone. But we depend on that phone for everything. It's our home telephone number. It's our work telephone number. And so that right there tells you the cost is going down. But in the old days, you had to do things so that, It's actually, now as a side comment, just because I thought about it, it's like the old days when we used to worry about syncing our address books. So if you wanted your phone to be dependable, the carrier would have to come out with software that would help you. If your phone died, transfer your names and your telephone numbers to your new phone. Now it's built in as a feature. It makes it dependable. Because, everyone has their life on their phone. So what happens if their phone gets in the rain and it shorts out? What are you going to do? This transfers automatically. This is all online. Or it's on a SIM card that moves over. But now we don't have to worry about syncing with, going back to the BlackBerry, with Outlook. The last BlackBerry I had synced remotely, wirelessly, to my computer and my Outlook. So I never even had to sync the thing. In the old days, it was a little cradle. You put the BlackBerry in the cradle. You needed the cradle so that customers would have that dependability as a feature so that they can depend on this phone being exactly the same as their Outlook on their computer, and everything was consistent and synced. The concept of syncing is going away. Actually, Google still uses the term, but everything is synced now. You don't have to sync anymore. We don't sync. In the old days, we sunk. We're syncing right now. Just kidding. Okay, you can probably read through the rest of this on your own. So in an attempt to make this more interesting for you, this is your assigned reading. Perceptions of reliability. Perceptions of reliability and availability specifications. Availability perceptions. I will go over the key points as a conclusion of this particular lecture. Dependability of the system reflects the user's trust in that system. It's a term used to describe a set of related non-functional system attributes. That's an important. Non-functional. Reliability is functional. So if you want to learn it this way, dependability is non-functional requirements. Reliability is functional requirements. Availability of the system is the probability that it will be available to deliver services when requested. Reliability. And the interesting thing, what makes it unique to software engineering, is that we don't have this in any other engineering topic. If the bridge is dependable, we don't have a likelihood of it not being dependable. Otherwise, we're going to have a lawsuit against us. Reliability of the software system. Reliability is the probability that the system services will be delivered as specified. And terminology we can go through. Again, human error, mistakes, system faults, system failures, faults and failures. If you want, there's absolutely more reading. There's absolutely no reason for me to go through this because I've gone through most of it already. Safety is a property. I did not define this one for you, I don't think yet. Reflects the system's ability to operate normally or abnormally without danger, without causing danger or harm, injury, death, without the damage of the system's environment. So is it going to cause injury? As I mentioned before, it's not necessarily human injury. It could be data injury or availability injury. It's injury of some sort, though. In terms of, we always think safety was injury. So. And it's important to consider safety, obviously. You put safety in the requirements. Safety requirements are often exclusive requirements, and usually they could be functional or non-functional. If safety in a heart monitor would be a functional requirement. In a pen, not very functional. The pen's still going to work even though it spills ink out all over the place occasionally. Not safe. Not safe for those. That would be safe harm to clothing. In the old days, you used to see, now you don't see that anymore. People used to put their pens in the pockets. Now there are no more shirts with any more pockets anymore because it's too nerdy. But you see big ink stains all over people's shirts. That's a safety issue. To laundry people. Alright, unreliable systems, we all know about that. Safety, accidents, security. So this is reading for you. You can go home and read all that stuff. So. And that was a 6B. Don't worry, we are going to break, don't worry. It is noon exactly. So I just want to bring up 6C to see if I'm going to cover it. Nope, I'm not going to cover 6C. 6C is all about dependability engineering. And I know you guys are probably sick of hearing the words already. This is where you're going to learn all the specifics. It's a repeat, essentially. In fact, what it is it takes the 6A, 6B, 6C, they're all A, B's, and C's, so they're all 6. Lecture 6. All talking about reliability and dependability. One focuses solely on reliability. One focuses, this particular lecture, number C, focuses solely on dependability. The one in the middle puts safety in there too, and it puts them both together. So, again, in lieu of a textbook, you have 50 slides there that you can go through and read everything you ever wanted to know about dependability. So what we're going to do is take a lunch break, a break, and then we're going to get into testing. So I'm going to talk about testing, because we need that. And I'm also going to talk about what's more testing. The testing is actually kind of short. It's not really that labor intensive. The testing will be maybe an hour and a half of testing or so. And then I want to talk about software costing, software estimating in terms of resources, cost resource allocation. We're going to go up through, I believe, and I'm just testing this real quick, up through lecture 11. After testing, so we have testing, costing, and then software. I'm going to end with the software architecture because you're going to need that most important. And software architecture is not really that bad. And then what ends up happening, and this is the same for the weekday. In fact, we just did lecture 10 in the weekday schedule. We're ending with lecture number 11, which I believe is still on architectural design. 12 through 17 are optional, building the software with reuse. One of them is going to be over agile software. One of them is going to be on distributed software. Another one's going to be on real-time systems. These are all of the little special topics that would be really good supplemental reading. I put optional next to them because I'm not going to cover them in the lecture, and they're not going to be the main points of the final exam either. The final exam the final exam is going to go up through lecture number 11. Let me just make sure 12. Hold on, let me just make sure. 12A, all the way through 12A, from 12B to the end of 7, just in case I don't see anybody after lunch here, from 12B through 17, not responsible for the final exam. It might help you with the midterm. Good reading might help you with the assignments as well, but not going to be covered content on the final exam. Final exam goes up through 12A, which is going to be the testing, the reliability, the dependability, all the and ending with software architecture. So let's break. How long do you guys want? 1 hour? Okay, good. We'll come back at 1 o'clock. And we're going to finish up today, which means we might stay until about 4-ish at the latest. Depends. We're not going to meet tomorrow, so don't worry about that. You do have to show for the final exam. The final exam is on April 30th, May 1st. The schedule is out there. If you don't like it, come up and see me. Or actually, it's better to send me an email message because we have a roster list. And just in case I don't see you, bring a student ID or your student ID number with you. Because only we will be checking people with their IDs so that we can make sure that only one person is taking one exam. And we have roster lists where we're going to mark you off. We're going to check you off the list so we knew that you came in. Believe it or not, in previous terms, I've had issues with more than one person going in like several times. I'm like, didn't I already see you? Didn't I see you already? And we have different forms. There will be 7 or 8 different versions of the exam. And as I mentioned, well, some people are actually taking it today. You guys only have the first half of the questions, believe it or not. I have a base of about 200 questions. You'll have about 25 of them on each exam, and there'll be different combinations, so randomly generated. So what I'm saying is you might have, in fact, yours was probably heavy on testing is what I'm thinking. I don't know. You might have some exams that have a heavy focus in one area and not cover everything because of the random generation of the questions. I'm going to have a final review session that will be recorded. I'll put the link in our weekend session. It'll give you the whole range of the topics with the lectures to read through and the information that you need to know about. Your exam that you get might be heavily focused in one area, or it might be a whole spread, or it might be heavily focused in a different area. All the exams will be different because there's 200 questions and you're only going to get 25 of them. So you're going to get a subset. So.
Is it like
pen and paper?
Next class, will we have the lectures first and
No.
then we'll go for
The next class, you only have to show up on one of the days, the Saturday or the Sunday.
just for the examination?
Yep, just for the exam.
Like 1 to 2 hours.
And the exam, or the time slots are in 2 hours. You guys will probably take about an hour or less. You guys took it. How long did it take you? 45 minutes? An hour? ish. Half an hour, easy. Well, don't worry about it. I'll talk to you guys in a minute. It will. You'll definitely finish it between 2 hours. When you're done with that, you can go. So you don't have to show up for both days. You just show up to take the exam. If you want, you can go through the lectures on each one of them. I'm going to cover everything actually that the weekday class is covered by the time we leave today. But I'm going to leave you with a lot more reading probably. So, because it's kind of, as a student, sitting here for 8 hours, 2 days in a row, it doesn't work. 1 day is enough. Questions?
Talk about midterm.
Before you came in, I talked about all that stuff. The 5 assignments, the midterm, and the CSLO.
So they're all May 9th.
I'm sorry?
They're all May
All
9th.
the due dates are May 9th for everything. Good thing for you is I've been recording. I'm recording right now too. So all you have to do is go back and you can see everything you missed from before you came in. Because it's all recorded. So you can go ahead and look at it. I went through the midterm, I went through the assignments. I think that's about it before you came in, maybe. I think you came in the middle of the lecture. Yeah, May 9th is the last day. You're going to take the final exam before you actually have the due dates for everything, before you have to turn everything in. If you don't like the weekend of the April 30th, if you want to take it early, I have one coming up on the 16th, 17th weekend. No, that's this weekend. I have one on the, nope, midweek. No, that's not this weekend. This is the 2nd, 3rd. I have the 16th and the 17th weekend open too. If you're a local student, you want to get it over with. Because some students are traveling. I use summertime. They're going back home. So if you want to take it the 16th, 17th weekend, I believe, look in the schedule. You'll see it. There's different time slots if you're local. Or even if not, if you're flying in, you can do it that way. And I have some people taking it today, actually, just so they don't have to come back. For accreditation purposes, you do have to take the final exam in person. And you are supposed to theoretically show up for 2 of the 3. So your name should be on a roster, hopefully, for 2 of the 3 sessions. However, if you take the final exam, that counts as 1. If you're here today, that counts as 2. So those people who aren't here today but were here last time, that counts as their 1, and they take the final. So.
And for also midterm, we need to be in person? Or?
No, the midterm is the take-home exam. And the midterm exam, you might notice, in fact, the TAs probably sent out messages saying that it was due on the 17th. It was, but that was for the weekday session. Your midterm exam's not due until May 9th at the end. And the CSLO is a completely different assignment than what we had last semester if you're a returning student.
No, I'm
Okay, you don't have to worry about that then.
not.
Any other questions before we break for lunch? We're going to come back at 1 o'clock, and we're going to go through all those lectures in about 3 or 4 hours maybe. We'll probably be out of here by 4, which is good. All right, thank you. I'll see you in an hour. Hopefully you'll come back.